Mars, the red planet. Introduction. Mars is the fourth planet from the Sun and the second smallest planet in our solar system, after Mercury. It is often called the red planet because of its reddish appearance, caused by iron oxide rust on its surface. Mars. Key facts. Position from Sun. Fourth planet in the solar system. Type: terrestrial rocky planet. Nickname: the red planet due to iron oxide dust. Size and structure. Diameter: approximately 6,792 kilometers, about half of Earth's. Approximately 12,742 kilometers. Radius: approximately 3,396 km. Surface area: approximately 145 million square kilometers, similar to Earth's land area. Mass: approximately 6.4 times 10 kilograms, about 11% of Earth's density. 3.93 grams per cubic centimeter, lower than Earth's 5.51 grams per cubic centimeter. Gravity: 3.71 meters per second squared, to 38% of Earth's orbit and rotation. Distance from Sun: 227.9 million kilometers, 1.52 astronomical units. Orbital period: year, 687. Earth days: approximately 1.88. Earth years. Rotation period: day, 24 hours 37 minutes, called a solar tilt. 25.2, similar to Earth. Ese 23.5 gives seasons. Moons: Phobos, larger, 22 kilometers across. Orbits: very close, slowly spiraling inward. Deimos, smaller, 12 kilometers across. Orbits farther out. Atmosphere composition: carbon dioxide 95%, nitrogen 2.2%, argon 1.6%, trace amounts of oxygen and water. Vapor pressure 1% of Earth's atmosphere at sea level. Weather: dust storms can cover the whole planet. Cold and dry climate. Temperature: average surface temperature -63 C, range from approximately 20 degrees Celsius daytime at the equator to -125 degrees Celsius nighttime at poles. Surface and landmarks: Olympus Mons, largest volcano in the solar system, approximately 22 kilometers. High Valles Marineris, giant canyon system, approximately 4,000 kilometers long, 7 kilometers deep. Polar ice caps, made of water ice and carbon dioxide ice. Surface and features of Mars. Color and composition: the planet looks red because its soil and dust contain iron oxide rust. Surface is rocky, dusty, and covered with craters from meteor impacts. Mountains and volcanoes: Olympus, monstrous volcano and mountain in the solar system. Height: 22 kilometers, almost 3 taller than Mount Everest. Base: 600 kilometers wide, comparable to the size of France. Other large volcanoes: Arsia Mons, Pavonis Mons, Ascraeus Mons, all in the Tharsis region. Canyons and valleys: Valles Marineris, huge canyon system stretching for 1,000 kilometers long, up to 7 kilometers deep, and 200 kilometers wide. So large it would span the entire United States. Formed possibly by tectonic forces and crustal stretching. Polar ice caps made of frozen water ice and carbon dioxide dry ice. Change with the seasons. In winter gives CO freezes, making caps grow. In summer gives CO sublimates, shrinking the caps. Impact craters: Mars has many preserved craters due to its thin atmosphere. Fewer meteors burn up. Largest impact basin: Hellas Planitia, about 2,300 kilometers across, 7 kilometers deep. Plains and deserts: vast plains covered in fine reddish dust. Frequent dust storms, sometimes planet-wide, lasting weeks. Ancient water: evidence dry river valleys, deltas, and lake beds show Mars once had flowing water. Minerals like clays and sulfates suggest water activity in the past. Today, water is mostly locked in polar ice caps and underground ice deposits. Atmosphere of Mars. General properties: extremely thin compared to Earth. Surface pressure is less than 1% of Earth's. Can't hold in much heat. Gives huge temperature swings between day and night. too thin to allow liquid water to remain stable for long. It either freezes or evaporates. Composition: carbon dioxide, CO, approximately 95.3% nitrogen, N, 2.7%, 1.6% oxygen, O, approximately 0.13% carbon monoxide, CO, approximately 0.08% water vapor, HO. Trace amounts, temperature, and climate: average temperature, tilde, 63 range, from approximately 20 degrees Celsius daytime equator to minus 125 degrees Celsius polar nights. Climate: cold, dry, desert-like. Weather and phenomena: dust storms. Most dramatic feature of the Martian atmosphere can cover the entire planet and last for months. Dust is very fine and stays suspended for long periods. Seasonal changes, caused by Mars's 25 tilt, similar to Earth's. Polar ice caps grow and shrink as CO freezes in winter and sublimates in summer. Radiation and protection: Mars lacks a strong magnetic field, so the atmosphere does little to shield from solar and cosmic radiation. Radiation on the surface is much higher than Earth's, one of the biggest challenges for future human explorers. Atmospheric loss: billions of years ago, Mars likely had a thicker atmosphere and flowing water, lost much of it due to weak gravity, hard to hold gases. Closing parenthesis, solar wind stripping away gases, no magnetic field to protect it. NASA's MAVEN mission confirmed that solar wind still strips particles from Mars's upper atmosphere today. Asterisk water on Mars. Asterisk past evidence: river, valleys and channels. Networks of dried up riverbeds suggest flowing water billions of years ago. Lakebed and deltas. Crater basins like Jezero Crater, where Perseverance landed, once hosted lakes. Minerals, clays, sulfates, and hematite, found by rovers, form only in water-rich environments. Shoreline features suggest that Mars may have had a northern ocean covering a large part of the planet. Present day. Water polar ice caps, mixture of water ice and carbon dioxide ice. Subsurface ice, detected beneath the surface across large regions, even near the equator. Salty brines. Extremely salty water may exist temporarily in liquid form under certain conditions, but not stable on the surface. Seasonal flows: recurring slope, linear dark streaks seen on slopes were once thought to be water flows, now believed to be dry granular flows, though briny water is still possible. Possibility of life past habitability: Mars was warmer and wetter billions of years ago, with lakes, rivers, and possibly oceans. Conditions may have supported microbial life, if it ever arose. Present conditions: surface is harsh, thin atmosphere, extreme cold, radiation, dryness. However, underground environments protected from radiation might still host microbial life. Methane has been detected in the atmosphere in small amounts, possible sign of microbial activity, though it could also be geological. Exploration and Search Curiosity rover found evidence of ancient habitable environments. Perseverance rover, collecting rock samples for future return, looking for biosignatures: fossilized microbial life. Future missions plan to drill deeper underground, where liquid water may exist. Asterisk past Mars gives very likely had liquid water and possibly habitable conditions. Present Mars gives water mostly locked as ice, with slim chances of microbial life in subsurface areas. Asterisk exploration of Mars. Detailed early missions. 1960s, 1970s Mariner missions. NASA. 1964 to 1971. Mariner, for 1965, gives first successful Mars flyby. Sent back 21 photos, first close-up. Images of another planet. Mariner 9 1971 gives first spacecraft to orbit another planet. Mapped 100% of Mars's surface. Revealed volcanoes, canyons, and dry riverbeds Soviet Mars program. Several attempts, with limited success. Mars 3, in 1971, achieved the first soft landing, but failed after 20 seconds of transmission. Orbiters and landers 1970s, 1990s Viking 1 and 2 NASA. 1976. First successful landers. Conducted biology experiments to detect life. Results inconclusive. Took panoramic images and studied soil chemistry. Mars Global Surveyor, 1996. Provided high maps and monitored weather patterns. Mars Pathfinder and Sojourner rover 1997. First rover on Mars. Showed mobility and surface exploration were possible. Modern robotic exploration 2000s present. Mars Odyssey 2001. Longest operating Mars orbiter. Discovered vast amounts of subsurface hydrogen. ESA Mars Express, ESA 2003. Discovered water ice and methane traces. Spirit and Opportunity rovers, 2004 to 2018. Twin rovers. Opportunity lasted 15 years. Found strong evidence of past water activity. Mars Reconnaissance Orbiter, 2006. Provided detailed imagery and discovered seasonal flows. Phoenix Lander, 2008. Confirmed presence of water ice beneath the soil. Curiosity rover 2012 present. Studying Gale Crater. Discovered ancient habitable environments, organic molecules, and seasonal methane changes. Maven Orbiter, 2014. Studying atmospheric loss to space. EXO Mars Trace Gas Orbiter, ESA Cosmos 2016. Searching for atmospheric gases linked to life. InSight Lander 2018-2002. 2. Studied Mars's interior using a seismometer. Marsquakes. Perseverance rover 2021 present. Exploring Jezero Crater. Collecting samples for future return. Searching for BIOSIGNATURES. Ingenuity. Helicopter 2021-2023. First powered. Flight on another planet. Over 70 flights. Far beyond expectations. International efforts. Scindia's Mongolian, 2013. First Asian nation to reach Mars orbit. Highly successful low-cost mission. China's Tianwen-1 mission 2021. Orbiter plus Jerome rover. First Chinese mission to Mars. UAE. Single quotes OS Hope Orbiter, 2021. Studying Mars's atmosphere and weather. Future exploration Mars. Sample return NASA and ESA. 2030s. Planned mission to bring Perseverance's rock samples back to Earth. Human missions. NASA aims for the late 2030s, 2040s. 4 crewed missions. SpaceX's Starship program is developing long-term plans for human colonization. Robotic missions in planning. ESAS, Rosalind. Franklin rover ExoMars delayed but planned for late 2020s. More orbiters and landers to search for water, life, and prepare for human arrival. Past exploration revealed Mars as a dry, desert-like world. Present missions show Mars was once wet and habitable. Future missions aim to return samples and eventually send humans. Mars and humans. Why Mars? Closest Earth-like planet in the solar system. Has day, length, 24 hours, 37 meters, and seasons. Similar to Earth, evidence of past water and potential HAB, ITAB, ILITY, seen as the best candidate for future. Human settlement beyond the moon. Challenges for humans on Mars. Thin atmosphere 95% CO. Almost no oxygen. Pressure less than 1% of Earth gives humans can't breathe without life support. Extreme temperatures average, -63 degrees Celsius, can swing from 20 degrees Celsius at the equator to -125 degrees Celsius at the poles. Radiation exposure. No strong magnetic field to shield from cosmic and solar radiation. Long-term exposure, dangerous for health. Gravity, 38% of Earth's gravity. Unknown. Long-term effects on bones, muscles, and human development. Dust fine. Sticky dust covers Mars, can damage machinery, clog equipment, and pose health risks if inhaled. Living on Mars habitats must be airtight, pressurized, and shielded from radiation, possibly underground, or using regolith as protection. Food and farming. Hydroponics and controlled environment agriculture would be necessary. Water supply, extracted from polar ice or underground ice deposits. Energy. Solar power is the main option, but nuclear power may be more reliable during dust storms. Human exploration. Plants and SA. Artemis program gives Moon as a stepping stone. Crewed mission to Mars targeted for late 2030s or 2040s. SpaceX Elon Musk's vision. Starship designed to transport large numbers of people and cargo. Long-term goal, self-sustaining. City on Mars. Other space agencies, ESA Europe, CNE, China, Roscosmos, Russia and ISRO India have expressed interests in future human Mars missions. Benefits of humans on Mars science. Humans can conduct faster, more complex exploration than robots. Survival. A colony could act as a backup for humanity in case of Earth-wide catastrophes. Innovation. Advancing space technology could benefit life on Earth and Mars. Exploration may unify humanity around a common goal. Living on Mars. Habitats and shelter. Pressurized domes or modules must keep in oxygen and maintain Earth-like pressure. Radiation protection. Mars has no magnetic field, so habitats need thick shielding. Options. Cover habitats with Martian soil regolith. Build underground bases or use lava tubes. Temperature control, insulation and heating required due to extreme cold. Water supplies, mining, extracting water ice from underground or polar regions. Recycling, closed-loop systems to recycle water from air, waste, and human use. Electrolysis. Water can also be split into oxygen for breathing and hydrogen for fuel. Food and farming. Hydroponics and aeroponics. Growing plants in nutrient-rich water or mist inside greenhouses. Martian soil regolith could be used with treatment, since it contains perchlorates, toxic chemicals. Protein sources could include lab-grown meat, algae, or insect farming. Closed ecosystem. Plants provide food and recycle carbon dioxide into oxygen. Energy and power. Solar power, primary source, but dust storms can block sunlight for weeks. Nuclear reactors provide reliable, continuous energy, fuel production, using Martian resources like CO from the air to make methane fuel for rockets, a process called ISRU, insight to resource utilization. Technology and daily life. Rovers and robots help build and maintain habitats. Spacesuits needed outside at all times. Thin atmosphere, no breathable air. Communication delay. Messages to Earth take 4 to 24 minutes one way. Health challenges. Low gravity. 38% of Earth's may affect bones, muscles, and circulation over time. Community and survivals. Small initial crews, 6 to 10 people, for early missions. Future colonies might grow into self-sustaining settlements with housing, labs, farms, and power stations. Social and psychological challenges. Isolation, confinement, and being millions of kilometers from Earth. Living on Mars would be harsh and demanding, requiring advanced technology, resource recycling, and teamwork. Yet, with the right systems, humans could one day survive and even thrive on the red planet. Challenges for humans on Mars. Thin atmosphere. Mars' atmosphere is 95% carbon dioxide, with less than 1% of Earth's pressure. No breathable oxygen gives humans need pressurized suits and habitats, too thin to block harmful radiation or keep liquid water stable. Extreme temperatures. Average -63 degrees Celsius. Range approximately 20 degrees Celsius. Equator in daytime to -125 degrees Celsius. Polar nights Habitats must be well insulated and heated. Radiation exposure. Mars lacks a magnetic field and thick atmosphere. Surface is bombarded with cosmic rays and solar radiation. Radiation increases cancer risks and can damage DNA, electronics, and equipment. Low gravity. Gravity is only 38% of Earth's long-term health effects unknown. But risks include muscle weakening, bone loss, changes in circulation, and organ function. Future colonies may need exercise routines or artificial gravity solutions. Dust and storms. Martian dust is fine, sharp, and electrostatic, gives sticks to everything. Contains toxic perchlorates, harmful if inhaled or ingested. Dust storms can last weeks and cover the entire planet, blocking sunlight, affecting solar power. Food and resources. Mars soil is not naturally suitable for crops. Toxic chemicals, little organic matter. All food, water, and air must be produced locally or transported from Earth. Self-sufficiency requires closed-loop life support systems and advanced farming methods. Building habitats must withstand low pressure, extreme cold, radiation, and dust. Likely need to be built underground, in lava tubes, or covered with regolith for protection. Communication delays. Signals between Earth and Mars take for 24 minutes, one way. No real-time conversation or remote control. Crews must be highly autonomous. Psychological and social challenges. Small crews, living in isolation and confinement for months to years. Risks of stress, depression, and conflict. Long travel times, 6 to 9 months each way, make rescue or resupply difficult. Living on Mars would push human survival to the limits. Thin air, deadly radiation, freezing temperatures, low gravity, toxic dust, and psychological strain. Overcoming these challenges will require new technologies, careful planning, and international cooperation. Human exploration plans, Mars preparation on Earth, and the Moon simulations and analog missions. Training astronauts in Mars-like environments. On Earth, for example, deserts, Antarctica. Artemis program. NASA. Establishing sustainable human presence on the Moon in the 2020s gives a testing ground for Mars missions. Technology, development, long-duration life support systems, radiation shielding, insight to resource utilization, ISRU, to make oxygen, fuel, and water from Martian materials. Crewed Mars missions, 2030s, 2040s, NASA's plan. First crewed mission, expected late 2030s or 2040s. Likely a small crew, 4 to 6 astronauts. Initial stays, approximately 30 days on the surface, gives eventually up to 500 days. Long stay missions, transport, rockets or SpaceX's Starship for faster, more efficient travel. Travel time, 6 to 9 months, one way. Surface habitats and bases. Landing sites, near water ice, easier resource extraction. Base design, inflatable or rigid modules, shielded with regolith. Greenhouses for growing food, solar and nuclear. Power plants for energy. Mobility, rovers for exploration. Possibly underground habitats for radiation protection. Building sustainability, ISRU insight, resource utilization, extracting oxygen from CO in the atmosphere. Already tested by Perseverance's MOXIE experiment. Mining ice for drinking water and fuel production, food production, hydroponics, aeroponics, algae, and lab-grown protein. Closed-loop systems, recycling air, water, and waste to minimize resupply needs. Long-term colony. SpaceX vision, Elon Musk, fleet of starships, delivering cargo and settlers. Goal, self-sustaining city of 1 million people within a century. NASA and ESA, more cautious. Science-focused outposts before large-scale colonization. China CNSA, ambitious long-term plans for a Mars base after 2033. Crewed missions, challenges to solve. First safe landing of large spacecraft on Mars. Thin atmosphere makes it difficult, reliable. Radiation shielding for long stays, affordable. Transportation systems for cargo and people. Long-term psychological and medical health in low gravity. Human exploration of Mars will unfold in phases, testing technologies on Earth and the Moon, sending small crews in the 2030s, 2040s, building bases with local resources, and eventually aiming for self-sustaining colonies. Success depends on solving radiation, gravity, and sustainability challenges. Asterisk. Benefits of humans on Mars. Asterisk. Scientific discovery. Humans can perform complex experiments and exploration much faster than robots. Ability to drill deep underground, collect diverse samples, and react to unexpected findings. Study Mars's geology, climate, and atmosphere to understand its past and present. Directly search for signs of past or present microbial life. Understanding planetary evolution. Mars once had water, thicker atmosphere, and possibly life. By studying why Mars became cold and dry, scientists can better understand Earth's future climate. Clues about planetary habitability help in the search for life beyond our solar system. Technology advancement, developing life support, radiation shielding, and sustainable energy systems will push technological innovation. New materials, robotics, AI, and medical solutions will likely benefit Earth industries. Advances in closed-loop recycling systems could improve sustainability on Earth. Survival of humanity. Establishing a presence on Mars creates a backup for humanity in case of global disasters on Earth, for example. Climate change, asteroid impacts, pandemics, closing parenthesis. Multiplanetary existence reduces the risk of extinction. Economic and industrial opportunities, mining Martian resources, water, ice, metals, and possibly fuel production. Potential for space industries like fuel depots and construction in the very long term. Mars could support trade and cooperation with Earth. Inspiration and global cooperation. Mars missions can inspire new generations of scientists, engineers, and explorers. Similar to Apollo missions, gives a unifying achievement for humanity, could drive international collaboration. On a scale larger than the International Space Station ISS, humans on Mars will bring scientific breakthroughs, new technologies, survival, security, economic opportunities, and global inspiration. While challenges remain, the benefits of expanding to the red planet could reshape the future of humanity. Humanity's next frontier. Mars is more than just a distant, red world. It is a window into our past and a bridge to our future. The towering volcanoes, vast canyons, and polar ice caps tell us that this planet was once geologically alive and possibly home to flowing rivers and lakes. Its thin atmosphere, freezing temperatures, and harsh radiation remind us of the difficulties that any human mission will face, yet also challenge us to push the boundaries of science and technology. Robotic missions have already revealed that Mars was once habitable and may still hold the key to understanding life beyond Earth. The search for water, organic molecules, and biosignatures continues, with each discovery bringing us closer to answering one of humanity's greatest questions: are we alone in the universe? For humans, Mars represents both immense challenges and unparalleled opportunities. Building habitats, producing resources, and surviving in such a hostile environment will demand innovation on a scale never seen before. But in overcoming these obstacles, we will not only expand human presence into the cosmos, but also develop technologies that improve life back on Earth. Ultimately, Mars stands as the most promising candidate for our species' next great step, whether as a scientific outpost, a new home for future generations, or a symbol of human resilience. The red planet embodies the spirit of exploration that has always driven us forward. As we look up at the night sky, Mars is not just a distant world, it is a reminder of what humanity can achieve when curiosity, courage, and determination unite.